ladies.
Hey, hi everyone, I'm Luke. I'm from the University of Sydney. I'm in a quantum theory group under Dominic Williamson and Professor Stephen Bartlett. This is not endorsed in any way by advisors. Okay, so let's get started. So we've all wondered what exactly makes a really good banh mi. Whether it's like how crispy the pork is, how good the sauce is. Hopefully in today's talk we'll be able to answer that. And in doing so, we will examine the universality of the so-called direct polymer in a random environment. Now, if that sounds totally crackpot, bear with me, because really this is actually a talk about universality, statistical mechanics. So in statistical mechanics, there's kind of this notion of universality where for a lot of really different looking models or lattices or problems, there's some notion that if you kind of coarse grain away these little microscopic details, you can actually end up in something called a universality class, where a lot of properties seem to be kind of independent of these like little microscopic details. And so there's really a more precise technical definition, but I'll just give a flavor of it. So basically, if you start from some Hamiltonian, there's some way to coarse grain that we call the renormalization group flow. And if you perform this kind of coarse graining, which sort of washes out these small microscopic details, you might have parts of that Hamiltonian that are irrelevant, relevant, or marginal. And if the irrelevant parts kind of like fall away as we coarse grain, you might end up in the same large scale Hamiltonian. And indeed, at like a phase transition, that you end up with a conformal field theory. Really what that's saying is, yeah, you kind of coarse grain everything out until there's like this scale invariant remaining Hamiltonian, you might think of it as. And so when we do this coarse graining procedure, really you might think like, all right, what actually matters? If there are these like microscopic details, generally it depends on kind of like the dimension you're working in. So like if it's like a 2-dimensional, 3-dimensional, n-dimensional problem, symmetries of the Hamiltonian that we're considering. So some symmetries might be like translationally invariant models. So if your Hamiltonian kind of looks the same, if you move it in space, there's like temporal, like reflection, a lot of different symmetries. These generally play into what makes the universal properties of a model. Any conservation laws and also boundary conditions are pretty important. So like what manifold that your Hamiltonian is kind of living on. Sort of as a spoiler for later, we're going to see that this problem that I'll lay out in what makes a good banh mi actually leads us into this so-called Kardar-Parisi-Zhang universality class, which is really intimately connected to this so-called Tracy-Weedham distribution. So this thing shows up like everywhere: finance, stochastic growth, wireless communications. If you've never heard of it, I'm not surprised, but really, if you know where to look, it really shows up everywhere. Okay, so let's get started. So the model that we're going to be considering is basically, we have some sauce that we're pouring onto the top of a banh mi, and we want it to like traverse a path through the sandwich and reach somewhere like on the bottom of the bread, right? So here's what the model that we're going to be considering. Effectively, our sauce starts at this origin, this 0, 0. And the banh mi has a width of L, right? So capital L. And the sauce has to like make a path through this filling. And the filling of the banh mi we're treating as really it's the potential. So you can think of it as like the regions with large potential are just kind of like dense fillings, and the sauce wants to like go around it. And regions with that low density of the filling are going to be low potential. And really this is the problem that we're going to be considering is, given the sauce starts at 0, 0, there's some potentially disordered medium filling the banh mi, and then the sauce takes a path and ends somewhere on the bottom of the bread, located at x minus L. Okay, so this is kind of the setup. So let's dive more into it. But first of all, here's just me performing some field research of origin and also okay, so that problem that we've set up naturally lends itself to directed polymer and random environment theory. So this was first proposed by Hughes and Henley in 1985. And basically the setup is as follows. So we imagine that we have kind of like a path that we need to take through some medium. And that medium in this case is, again, just like going to be the filling of the banh mi. And that filling of the banh mi, we parameterize by some environment potential that we call V of x and t. Now, I'm going to use the coordinates x and t as convention, but really you should be thinking of the x-axis as kind of like the position and t as sort of like the y direction. So it's going to like traverse in the negative t direction and then somewhere along this sort of x-axis. Okay, so the path that it's going to take is called gamma. So this gamma is going to be a series of points that the path takes. And this path that we're going to consider is going to be living on a lattice. So we're going to consider discrete points, not continuous, just for the time being. But we'll see that a continuum theory eventually emerges. And so the path that it takes is parameterized by this like x naught, x1, up to xl. And another condition that we're going to enforce is that we start at the origin. So x naught is like at 0. And every subsequent point in time, or meaning like as we go down, it's either going to move to the right one step or to the left one step. So that's just what that second condition is saying. And also really important is that because it only moves down left or right, the sauce can't like go up. So it's how we go against gravity. So, and that's also the no overhang condition. So that's actually required for this stat model. Okay. Now, the next thing we need to consider is actually the energy cost of our sauce traversing through the medium. So this is going to be the Hamiltonian that we write down. So it's just a function of the path taken, and it's really just the sum over the potentials experienced by the sauce, like at each point. That makes sense. And please stop me if anything's not clear. This is intended to be pedagogical. Finally, we assign a Boltzmann weight according to each path that the sauce can take. So really the sauce wants to pick the paths of least resistance, right? So that's going to be sort of the lowest energy. But the probability of the sauce taking some path is proportional to this Boltzmann factor here. Has everyone taken statistical mechanics? Or no? Okay. Basically, yeah, see a StatMech textbook, but basically you just have some, yeah, there's some proportion, yeah, it's the probability is associated with this Boltzmann factor here.
What's the physical meaning of beta parameter here?
Beta is the inverse temperature. Thank you. Sorry, I forgot that. So yeah, beta here is just like 1 over the temperature, and we're working in units where the Boltzmann constant is 1.
The temperature here is the actual room temperature, not some effective.
No, it's an effective temperature. And we'll see where that plays in just a moment. So here are some lattice simulations that I ran of the sauce traversing from the origin in some disordered medium and reaching somewhere on the bottom of the bread. So imagine this is like the bottom of the bread. Here's the top of the bread, and that's like the origin where we're like squeezing the sauce in. Now what we're sort of as an approximation, we're modeling the banh mi filling as a Gaussian distributed potential, which is probably not realistic, but you know, it's still a first approximation.
It's a large enough banh mi.
Yeah, perhaps negative potential would be kind of weird. I don't know if that was a black hole in there or something. Anyway, what are we doing now? Okay, so. Also, this is called a point-to-line polymer. So because the sauce is fixed to start at the origin and end somewhere like along this line at the bottom, that's what it's called in literature. So if you look up point-to-line polymer, we start at 0, 0, and we end somewhere at xl minus L, and that endpoint is allowed to be free. So I ran these simulations with lattice that's 96 by 96, lattice points. And this is at 0 temperature. So exactly what you're asking. Really what the sauce is doing in this 0 temperature limit is it's picking like the optimal channel to end somewhere on the bottom. At finite temperature, the sauce is going to traverse multiple paths, but because we're at zero temperature, it just picks out the ground state configuration. So it's just finding the minimum energy channel to like end somewhere. But you can see that this kind of like speckled looking strangeness, that's just sampling new environments. So you can think of like multiple banh mi's being made, and each one is a different disordered instance environment. And then from that specific banh mi, we try to find like the optimal path. Okay. What happens when we're at finite temperature? Well, in this case, many sauce paths contribute. So if you've heard of like a path integral, this is kind of what we're getting at here. But really, we need to define this partition function. So again, please see a StatMech textbook. A partition function is just a weighted sum over all possible configurations of a system in which the configurations where the energy is lower contribute more strongly to the weighted sum. And the partition function includes all the thermodynamic properties of the system. So in our case, we have this weighted sum over all possible paths that the sauce can take, starting at the origin, ending somewhere on the bottom of the bread. And from that partition function, we can define the point-to-line free energy, which will be important later, but really it's just negative the logarithm of this partition function divided by this inverse temperature. So you can think of it as just multiplied by like T. And if we sample enough of those disorder realizations, so we sample a bunch of the banh mi's being made, and then we compute this free energy associated with like the paths that the sauce can take, and we normalize it, we end up with this kind of histogram here. And I've overlain this black curve on top of the yellow samples. So this is 1 million disorder realizations of a 256 by 256 lattice. It took a while. And the yellow results are like this distribution over this free energy cost of the like sauce to traverse somewhere. This black curve, this GOE Tracy-Weedham, appears that I've pulled it out of a hat, and it comes from random matrix theory. Where does that come from? Find out later in this talk. But for now, it's, just observe that we have this strange looking shape. But I'll talk about more where that actually comes from. Okay, so now we have this directed polymer in a random environment where you have some polymer that starts somewhere and ends somewhere along the line, and it traverses some random environment. You know, this potential can be like positive or negative or in between. How do we actually solve this? Well, lucky for us, some mathematicians that were awarded the Fields Medal a couple decades ago realized that we can actually solve this equation if we first consider the inverse Cole-Hopf transform. So as before, this Z is the partition function of a polymer starting at the origin and ending somewhere at X on the like this axis and T kind of on the vertical axis. And we instead define this height transformation, this H of X of T. So it's just like the logarithm of the partition function. So really it's just proportional to like the free energy you can think of. And what's nice is if we write this transformation down and then we take the continuum limit, meaning on the lattice, we kind of take the lattice spacing to like 0. I think particle physicists consider it a different way, right? It's like you make the lattice infinitely big.
It's the same thing.
I think StatMech way is cooler. So. We're going to take the lattice spacing to 0.
Oh, because you can boundary conditions.
That's true. Okay, anyway, that's not really important for this talk. Okay, so we just assume there exists some well-defined continuum limit. And if we take that continuum limit, then the solution must be given by the solution of this stochastic equation. So this equation right here defines the so-called Kardar-Parisi-Zhang universality class. So what I hinted at the start, there's this Kardar-Parisi-Zhang universality class where a bunch of like different looking problems sort of all kind of flow to this behavior. And it's named after the 3 guys that wrote down this equation. And in this equation, so it's a nonlinear stochastic equation. The first term is dth, that's like the partial derivative of the height with respect to time. This is the second derivative with respect to space of that height. This lambda is just some constant, and this is the nonlinear part. So this is really what makes it kind of tricky to solve because it's like a nonlinear equation. But it's, yeah, just the square of the partial derivative with respect to space. And then finally, that disorder that we have, so that random environment that it's kind of traversing, that's just like encoded by this I slash xi, I think. I. Yeah, and so we take that to be space-time white noise. But even if we don't take like Gaussian disorder of our potential, we can see that this still like really well encodes the behavior of the system. That's why it's like a universality class. So kind of these microscopic details get washed out. Okay, so now we have our directed polymer in a random environment, which is trying to model the sauce through the sandwich. We've taken that directed polymer in a random environment and we've mapped that to the Carter, Parisi, Zhang universality class. What do we actually get from that mapping? So the predictions from the KPZ universality class basically tell you that the free energy cost of that polymer or that sauce channel, effectively you get like a linear term in the length, like how deep the banh mi is, where this sigma is just kind of like a surface tension or something. Then we have like a L to the 1/3 characteristic term. So that's kind of like the fluctuations about this like deterministic part. C here is another just constant. Gamma is also a constant, just ignore that. And then chi is the important part. So chi follows a Tracy-Weedham law. So all the randomness, like the distribution over our free energy costs are kind of encoded by the distribution of this chi. And that chi depends on the boundary conditions. So if we fix like the origin and we let the endpoint go anywhere along this line, that's called point to line. If we fix the origin and we fix the endpoint, that's called a point-to-point polymer. And there's other boundary conditions you can impose. But basically, those boundary conditions tell you what type of Tracy-Weedham distribution this chi follows. And on the right, this figure is just what like a Gaussian distribution looks like. So if you've ever heard of like the central limit theorem, a lot of things flow to this Gaussian universality class. But whenever you have kind of correlations between your variables, then oftentimes you'll end up with this Tracy-Weedham distribution. And the defining characteristics of the Tracy-Weedham distribution is kind of like a non-zero skew. So it's sort of like, you know, shift to the right a little bit. And the tails are well characterized by really smart mathematicians that I don't understand their work. Okay.
So what's the physical meaning of this unit?
Thanks, that's a good question. Forgot to say where this actually came from. So this distribution actually comes from random matrix theory. So if you take random Gaussian orthogonal matrices and then you just look at the largest eigenvalue, the distribution of that largest eigenvalue follows this guy. So it seems like, I don't even know why they're related, but they just seem to be. So the skew is kind of just saying that you're more likely to be on the right tail than the left. Physically, I don't really know why. That's some math mystery. Yeah. Okay.
I might have completely missed this, but what is the physical meaning of some of those constants?
So sigma is kind of like a surface tension. You can kind of think of it as. C is just like how strong these random fluctuations behave. And gamma is just some subleading correction. Like it's just some random constant. It depends on the microscopic details. So really the universal thing is just this chi. Yeah. Okay, so so thus far we've seen that this Tracy-Weedham arises from this directed polymer in a random environment, which we claim models like sauce traversal of a banh mi. Now, let's see that it actually shows up in error correction. So this entire time you were listening to a quantum error correction talk. Okay, so in quantum error correction, we can write down, again, like a statistical mechanical model. I'm not gonna explain this Hamiltonian, but just know that there exists a nice way to encode decoding of quantum error correcting codes using statistical mechanical models. So if you have like a quantum error correcting code, you have your little qubits like sitting in some array or whatever, and then noise can like induce errors onto it, right? So the universe can conspire to like send a cosmic ray and like flip the qubit or something. I mean, it's like thermal noise too. Anyway, when that happens and you have these kind of errors acting on the system, you can kind of think of it as like the disorder acting on the statistical mechanical model, right? And there's a concrete way to write it down, but basically, yeah, if you write it down, you obtain this random bond Ising model, which is it's just like a 2D Ising model, but you kind of like let the coupling constants be positive or negative. That's all that's important here. And what's important is if you then simulate like the failure rate of a surface code, which is like the most common quantum error correcting code, and you define this StatMech model in the canonical way, then you obtain free energy costs of your logical operators. So your logical operators in a surface code is just like a string of like Paulis that like wraps around the torus. And as you might expect, that logical operator, that string, is exactly traversing that like random environment, right? Exactly like the banh mi in the sauce. So we can play the exact same game. We can write down what the free energy cost of this logical operator is. And if you do it and you work through the details, you obtain exactly the same Tracy-Weedham distribution, which may be surprising, I don't know. And this is only in a really simplified model, so code capacity quantum error correction. And so the argument would then be like, okay, sure, you have this nice little toy model. Does it actually show up also when you actually have like real experimental data? And so just remember that Tracy-Weedham, this. Here's like the actual practical circuit level noise. And you can see that it actually has like the same behavior. So it really does seem like this universality class that we've kind of identified really does show up in nature a lot. And so in summary, a good banh mi is really a problem in disordered media. Directed polymers is like the nicest minimal physics model. Large-scale behavior is universal, as we've seen across a bunch of other things. Indeed, it shows up in like a ton of other stuff too. But boundary conditions matter, and also that same domain law logic appears in quantum error correction. Thank you.
Any questions?
Surely a good banh mi is one of the sauce,
Yes, but it's a multivariate optimization problem, and we're only considering one variable here.
So let's thank Luke again. I hope you all think of KB